Good morning, my dear students. My name is Dr. K.C.H. Apparao, working as a associate professor in mechanical engineering department. Today, I would like to discuss on critical thinking questions on fins. We'll see first of all how to derive the rate of heat transfer formula in fin in rectangular fin. So, in rectangular fins are three types. We will see three types of rectangular fins. One is the long fin, second one is the insulated end fin, and convection of the end fin also we'll see. So here we'll see first for the long fin. So first of all, we'll see what is the importance of fins and what is the general equation, right, of heat transfer equation for the rectangular fin, particularly long fin. Okay, you know this one fin is the suppose whenever the available surface is found inadequate to transfer the required quantity of heat. So with the available temperature drop and convection heat transfer question. So extended surfaces we add. Suppose this is the any surface of any engine. Suppose you know this one engine surface, because for in conduction and convection heat transfer takes place in two modes. One is the conduction, another one is the convection. Conduction means surface to surface. So in this surface, that is the conduction process, and the convection means from surface to atmosphere, that is the convection process. In both cases, you know the conduction process formula Ka into delta T by L. Convection process is equal to HA into delta T. Okay. So in this area, suppose the heat transfer between the engine to atmospheric air means atmospheric temperature. We can't change or we cannot influence the atmospheric temperature. So we cannot change the temperature difference. So in those cases, thermal conductivity K, that is the property of the material, we can't change it. Thickness also, that is indirectly to heat transfer rate. We want to just like if you want to increase the rate of heat transfer, so you know that Q is directly proportional to area. It means if you increase the area, effective area, automatically the rate of heat transfer will be increases. Okay, so that is the main. Whenever the available surface is found inadequate, so here in the surface of any engine, the surface is inadequate to transfer the heat uh, through temperature droplet and convection heat transfer through surroundings. Okay, so in this case, we add some external surfaces or extended surfaces to increase the effective area. If the effective area increases, automatically rate of heat transfer will be increases. So for this purpose, based upon this purpose, we add some rectangular pins on these surfaces like this one. Okay, if you add this type of external fins, extended surfaces on this engine body, automatically heat transfer rate will be increased. It means heat dissipation from the uh, engine to atmosphere will be increased by adding these external surfaces, because of this reason. If the effective surface increases, automatically rate of heat transfer will be increased. Okay, so in conduction process also, in convection also. Okay, so mm, for this reason, based upon this reason, we add some external surfaces to the main surface of the any body where heat dissipation is required. Rate of heat transfer will be required for the cooling purpose, any purposes. So you know the best examples of external means cooling of the transformers. We will see some types of fins on the transformers for heat transmission or heat dissipation or heat dispersed from the engine surface. And in some cases, just like fins, rectangular fins placed on the some engines to uh, for the cooling purposes. Some types of rectangular fins placed on the motor engine, motorbike engines for the cooling purposes. So many areas of many applications of fins are there. We can see the fins which are attached on the compressors to decrease the rate of it means to decrease the surface temperature of the engine also. Okay, we'll see the functioning of heat transfer in the fins. We derived the rate of heat transfer in the fin also. Okay, we'll see first of all. You know that heat transfer by convection between the surface and the fluid surroundings. It can be increased by attaching the thin strips of metals. Those are called fins or extended surfaces. Because you know that the fin increases the effective area. Effective area is directly proportional to rate of heat transfer. If the effective area increases, automatically rate of heat transfer will be increase by convection process. Okay, we'll see first. We'll derive the critical thinking question, that is derive the expression of heat transfer in fins in case of rectangular plate. Okay, we'll see uh, how to find the rate of heat transfer in rectangular fin. So this is just like this one is the rectangular uh, fin which is attached to the main surface of any engine. So we can assume this one, this is the surface of the any engine. So here rectangular plate is attached to this surface. Then the initial temperature of this surface of the engine or surface of the any uh, body. So that is T naught. Uh, So we know that initially we'll consider some rectangular small elemental area. We derive the formula for the small elemental area. Then we integrate that one. We'll get the uh, rate of heat transfer throughout the pin. Okay. So for solving the rate of heat transfer in this pin, just here also I'm considering small elemental area. So that is which is distance x from the main surface of the body. So this is x distance. The thickness of this small elemental area is equal to dx. Okay. So qx is the rate of heat entering into the element, and qx plus dx, this is the rate of heat leaving from the element by conduction process. Similarly, q convection, that is the rate of heat leaving from this elemental area through convection process. It means the Qx rate of heat entering into the element is is dispersed by through modes. One is the conduction process, another one is the convection process. Okay. We'll consider this one. The length of this fin is L. The thickness of this fin is equal to W, not width of this fin is equal to W. The thickness of the fin is equal to T. Okay. So then the area of end surface, that is the area of the end surface of the fin is equal to W into T. You can consider this one. Okay. Thickness is equal to T. Then elemental area. So you can take this one, small elemental area. Thickness is equal to dx, and throughout length, perimeter of this one you can take, that is the 2 into w plus t, you can take like this one. Okay. So heat balance for the element. First of all, we already told that heat entering into the elemental area is equal to heat dissipated by two modes through conduction mode, another one is the convection mode. Okay. We'll derive this one. So you know the formula. So this is conduction minus k into dt by dx according to Fourier's law. So this is nothing but minus k into dt by dx plus minus k into, it means minus k into One is dt by dx plus another one is d square t by dx square. So for x plus dx, okay, derivative of this one. So minus ka dt by dx minus ka into d square t by dx square into dx. Okay. So plus q convection. You know the formula HA into HA into temperature difference. So temperature, just we are taking an elemental area here. So at distance x, the temperature at a particular elemental area, that is the temperature T, and the distance x, and the area is equal to, you know that area is equal to, so perimeter of this pin into dx, p into dx. So perimeter, you know that perimeter is equal to, so width into thickness 2 times 2 into w plus t thickness. Okay. So you know that perimeter. The formula is equal like this one. Hp, this is the area p into dx of the small elemental area. Temperature difference T minus, so T infinity. T infinity means ambient temperature. So then this will be cancelled. Then the formula will be like this one. Is equal to 0. Then if you take T minus T infinity is equal to theta. Okay. Integrate this one both sides. dt by dx is equal to d theta by dx. Okay. So then in t place, then you can write to theta. Then the final formula is called like this one: d square theta by dx square minus m square. M square means hp by kl. So we are taking for the simplification, you can represent this hp by ka is equal to m. Okay. So then m square into not this one, under root of m is equal to under root of hp by k. Okay. So m is nothing but under root of hp by k. Then you can m square is equal to hp by k. Okay. Just you are taking this as m square theta. So this is the theta, d square theta by dx square minus m square theta. So this is the you know that was the second order linear equation. If you integrate this one, we will get to general equation. That is the general equation is equal to theta is equal to c1 into e to the power of minus mx plus c2 into e to the power of mx. This is the general equation. So this general equation will be used to find the rate of heat transfer in different types of the rectangular pins. One is the long pin, another one is the insulated end pin, second one is the convection of the end pin also. Here in this, we'll see, just I'm taking the long pin. So this is the long pin. So long pin means these types of pins have different types of boundary conditions. We'll see the boundary conditions of this long pin. Okay. At x is equal to 0, t is equal to t naught. You know this one. This is the t naught temperature. But this is the long pin means very long. We can represent this one x is equal to infinity. At x is equal to infinity means it means very long fin means at the end of the fin, the temperature of the end of the fin is nothing but that is equal to atmospheric temperature almost. So this temperature is equal to T infinity. It means at x is equal to infinity, temperature is equal to T infinity. That is the condition. If you apply these two boundary conditions, we will get the rate of heat transfer in a long fin by using the general equation, okay, which was derived in previous slide. Okay. So for long fins, infinitely long, we are assuming this one. Then length tends to infinity. If the fin is sufficiently long, the temperature at it ends equal to surrounding fluid temperature. It means here temperature is equal to T infinity. Okay. Just we are taking some distance x, that okay, small elemental area dx at that distance, so temperature is equal to T. Same formulas. Okay. Derive this one. So apply the first boundary conditions. in general equation and apply the second boundary condition in general equation. Then we'll get the C1 and C2 values. Then these two C1 and C2 values should be substitute in the general equation. Then we'll get the final equation, temperature equation for that small elemental area. Okay. Uh, just here we are applying the second boundary condition first of all. Second boundary condition. What is the second boundary condition? At x is equal to infinity, theta is equal to T infinity minus T infinity. Okay, so that will be 0. So temperature difference is equal to 0 because the last end temperature of that fin is equal to atmospheric temperature. Okay, if you substitute this one, C1 e to the power of minus infinity plus C2 e to the power of m infinity. Okay, so you know that e to the power of minus 1 by infinity is equal to 1 by e to the power of m infinity. This value is equal to 0. This value will be 0. Then C2 e to the power of m infinity is equal to 0. You know that e to m infinity, it is not equal to 0. It must be a particular value, some value. It has some value. So it should not be equal to 0. It would not be equal to 0. Then automatically you can understand that one C2 is equal to 0. So C2 is equal to 0 because e to the power of m infinity is not equal to 0. Okay. So from this one, we got this one C2 is equal to 0. Then apply the second boundary condition. To apply the second boundary condition, not second, the first boundary condition. So what is first boundary condition? At x is equal to 0, theta is equal to theta naught, T naught minus T infinity. Okay. T naught is the temperature of the base temperature. So C1 e to the power of minus m0 minus C2 e to the power of m0 is equal to theta T naught minus T infinity. So here m0, so C2 is equal to 0, this will be 0. Then C1 e to the power of m0 is equal to T naught minus T infinity. Then C1 is equal to because the value of e to the power of minus m0, e to the power of 0 is equal to 1. Okay. Then C1 is equal to T naught minus T infinity. So T naught minus T infinity you can rewrite like this one, theta naught. Okay. Then you know the value of C1 and you know the value of C2. Substitute these values in general equation. So T minus, will get this formula finally. T minus T infinity is equal to theta naught minus T infinity. T naught minus T infinity. You know that theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. This is the formula. Theta is nothing but T minus T infinity is equal to C1 value. You know that value of C1, C2 is equal to 0. C1 is equal to theta naught, T naught minus T infinity into e to the power of minus mx. So this is the value. Okay. So we can rewrite like this one. This is nothing but theta, this is nothing but theta naught. You can rewrite like this, theta by theta naught is equal to, otherwise T minus T infinity by theta naught minus T infinity is equal to e to the power of minus mx. Okay, this is the formula. If you want to find the temperature at any particular distance, then you can use this formula. Okay, then we will find the, by using this formula, you can find out the heat transfer in the long fin by using convection process. You know that convection process. You know the convection process. HA into dx, HA into d theta. Okay, d theta. So delta T or HA into delta T. Temperature difference is equal to E minus T infinity. Area is equal to area of the small elemental area, that is P into dx. You know this one, HP dx into T minus T infinity. Okay. So you know the limits from 0 to infinity because this is the long pin. So limits is equal to 0 to infinity. If you apply the limits, then if you integrate this one, you will get the rate of heat transfer formula. Then Q is equal to 0 to infinity HP into T minus T infinity into dx. If you integrate this one like this one, integrate this one, you will get like this, because e to the power of minus mx is equal to minus 1 by mx into h theta hp into just to, if you apply the infinity, that will be 0, then if you apply the 0, that will be 1. So the formula is will be like this one, hp theta into uh, theta naught into e to the power of minus mx. Okay, then the formula is equal to, so 1 by m into hp theta naught into 1 minus 0. The final formula is like this. So P is equal to, because you know the value of m is equal to under root of hp by ka. If you substitute this value here, then this is the value. P is equal to under root of hp ka into theta naught. Theta naught is nothing but T naught minus T infinity. Okay, this is the final formula. Then we'll see one more numerically based upon this formula. Calculate the amount of heat energy required to solder through two very long pieces of base copper. Diameter of the wire also given. Okay, with solder that the metal at the temperature, so T naught is given. The wires are positioned vertically at the air. So T infinity is equal to 20 degrees Celsius. T naught is equal to 190 degrees Celsius. Okay. Assuming that the heat transfer coefficient H also given 20 watt per meter degree Celsius. Thermal conductivity K also given. K is equal to 330 watt per meter. Okay. So calculate the amount of heat required to solder this one. You know the formula theta is equal to. So what is the formula? Q is equal to under root of hp k into theta naught T naught minus T infinity. So these values are given. H is the rate of heat transfer given. K thermal conductivity given. Area is equal to 5 for d square. D also given. D is equal to 1.5 meters converted to meters 0.0015. Okay. So P is the perimeter. Perimeter is equal to 5d. You can take it one. So if you substitute all the values here, then we will get the answer 2.252 watts. Okay. One more numerical we'll see. In an experiment to determine the thermal conductivity of a long solid 2.5 diameter rod. So diameter of this rod is given. That is the D is equal to 2.5 centimeters. It means 0.25 meters. Its base is placed in a furnace. A long portion of it protecting into the room temperature. Room temperature T infinity, ambient temperature 22 degrees Celsius. Okay. After steady state conditions prevail, the temperature at the 2 points, 10 centimeter apart. So just like here, this is the solid surface. Here temperature is equal to T naught. At the distance of 10, this is here. Here temperature is equal to 85 degrees. So two types of temperatures are given. At a distance x, temperature is given. Okay. So next we have to find out the convection heat transfer also given. Determines the thermal conductivity of the material. K, you have to find out the K value. Okay. So for this one, temperature profile difference, we have to consider this one. Then based upon this one, you can find out the M value. By using the M value, you can find out the T value. Okay. Here already given. Just temperature profile, you know that theta by theta naught is equal to e to the power of minus mx. X is equal to 10 meters. Distance are given 10 centimeters. It is the 0.1. Okay. Theta is equal to T minus T infinity. One temperature is equal to 85. T infinity ambient temperature is equal to 22. And T naught minus T infinity. So the initial temperature, base temperature is equal to 110 minus 22. So all the temperatures are given. You can take e to the power of minus m into x value also given. So from using this formula, you can find out the m value. That m value is equal to 3.34. Okay. So if you know the m value, you can find out the thermal conductivity K value, because m is equal to under root of hp by K. Okay. Then m square is equal to HP by K. Then K is equal to HP by M square into area. So perimeter P is equal to pi d. Diameter is given. Diameter is equal to 0.25 meter square meter, and area is equal to 540 square. So like this one. This is the area. This is the pi d value. Perimeter value. If you substitute these values, then you will get the thermal conductivity. So thermal conductivity of that material is equal to 406.5 watt per meter Kelvin. Okay. So these are the different textbooks. You can refer this one for solving different numericals which are based upon the fins, particularly long fin. Next class we will see few more fins, insulated end of fin, next to convection of the fin. We'll see. We'll derive those formulas also. We'll solve the numerical based upon those fins also. Thank you for watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.